Alright, so in this video, I wanted to take a look at another type of calorimeter, a little bit more fancy than the coffee cups that we saw before, and this is a bomb calorimeter. So the diagram right here shows what's going on inside one of these bomb calorimeters. Basically, you have like a steel bucket, and inside that bucket is a little chamber where you can keep a reaction. And surrounding that chamber is water, which also has a thermometer in it where you're able to then track the temperature change of the water throughout a given reaction. This is especially helpful for combustion reactions where you want to have all the heat from the combustion transfer to water around it. But in order to burn something, right, you can't really have like water actually in there. So the actual reaction itself is kind of contained in this little cage at the very center of the water. And so that's where we really carry out the combustion process, allowing heat to escape to the water surrounding it. And in these bomb calorimeters, it is like a steel cage that the reaction is being kept in. And for that reason, then there's no expansion work done at all from this reaction. So although combustion may produce gases like carbon dioxide and water vapor, right, those gases are not going to expand their container at all. And as a result of that, right, there's no work involved in this reaction that we measure, which is to say that all of the heat that is transferred from the reaction to the surroundings is exactly equal to the change in energy of the reaction. So right, usually difference in energy depends both on heat and work. What we're saying with this setup is that volume is being held constant, so work isn't actually involved in this at all. Now while this bomb calorimeter is a little bit fancier than the coffee cup calorimeters that we saw previously, in principle, they still operate in a pretty similar way. The only major difference is that with a bomb calorimeter, you typically don't have a, say, specific heat capacity that depends on like the mass of the surrounding water or anything. Instead, the calorimeter itself has a heat capacity, no specific in there, that represents the heat required to raise the temperature by 1 Kelvin or 1 degree Celsius. So right, we kind of take the mass element out of here so that the heat transferred to the surroundings is simply equal to the heat capacity times the difference in temperature. So if we're given a heat capacity that's maybe in units of joules per Kelvin or kilojoules per Kelvin, right, the grams are not included in there because mass isn't actually required for that calculation. But that's really like the only major difference between the bomb calorimeter and the coffee cup calorimeter. Again, in certain applications, this bomb calorimeter is very helpful. So let's look at one example where we can use the bomb calorimeter to maybe determine things like the enthalpy of reaction or, in fact, the change in energy of reaction. So I describe here a scenario where a bomb calorimeter has a heat capacity of 12.76 kilojoules per Kelvin. And inside that bomb calorimeter, I initiate this combustion reaction of C2H2. I take 2.5 grams of my fuel and I ignite it. And as a result of that, right, the temperature of the water immediately surrounding the reaction chamber raises from 23.5 degrees Celsius to 33.3 degrees Celsius. And so my question for this is, what is the change in energy of reaction for this combustion, where I have 2 moles of C2H2 plus 5 moles of O2, producing 4 moles of CO2 and 2 moles of H2O? All right, so this is again similar to maybe some of our previous examples. In this case, the only real difference is just how we calculate the heat of the surroundings, that is like the heat of the calorimeter. But take a moment to try to work this one out, give it your best shot, and then I'll go over it in a little bit. Okay, so for this reaction, what I found is that the change in energy, or the delta E of the reaction, is equal to negative 2600 kilojoules per mole. And I want to show exactly how I did this. It's a very similar process to what we had seen before with the coffee cup calorimeter. Basically, we break down this problem into 3 steps, where we want to first find the heat of the calorimeter itself. We then know that the heat of the reaction is equal to the negative heat of the calorimeter. And then finally, our enthalpy of reaction, which is just equal to the energy of reaction in this case, is equal to Q over N, that is like the heat of the reaction divided by the number of moles of the reaction. So to walk through this, again, kind of step by step, I'm first going to find the Q of my calorimeter, which is done using its heat capacity, 12.76 kilojoules per Kelvin, times its difference in temperature, that is 33.3 degrees minus 23.5 degrees. And when I evaluate that out, I get a heat of 125.05 kilojoules. Now, technically speaking, this heat should be reported to two significant figures. It's not obvious from the way that it looks as I've set up the calculation right here, but keep in mind that when we calculate that difference in temperature, right, or delta T, that difference can only be reported to the tenths place because of how our initial and final temperatures are to the tenths place. And so even though I've written it out right here and all of my initial and final temperature have like three significant figures, right, technically speaking, the delta T that is taken from those is only 9.8, right? That is like 2 sig figs as delta T. So I kind of bolded right here just how many significant figures are actually significant in my answer. But because I'm doing a continued calculation, I'm just going to kind of make a note of those 2 sig figs and then round off at the very end of this calculation. But all of that is to say then that the heat of the calorimeter is about 125 kilojoules. That then means that the heat of the reaction is just negative 125 kilojoules. And so I now have part of my delta H reaction calculation done, right? I just need to find now the moles of the reaction. Now in the last example that we did with like the sodium hydroxide, we had started with our grams of NaOH and then simply converted that into moles. So in this case, we have C2H2 instead. I'm starting with 2.50 grams of that. I can then convert that into moles using its molar mass, which I found right here. And last time, that was kind of it, right? That told us then the moles of the reaction. But if we look very carefully at the balanced chemical equation that is provided to us, we can see that the C2H2 has a molar coefficient of 2. And so what that means then is that the moles of the reaction is not actually equivalent to our moles of C2H2. Instead, for every 2 moles of C2H2, there's 1 mole of the overall reaction occurring. And so I've kind of arranged a conversion factor like so, basically finding, instead of just moles of C2H2, moles of reaction, using the molar coefficient to kind of relate the two. So what that means then is that our N here, or our moles of the reaction, is actually equal to about 0.048 moles, and it's that number then that we're going to use in our delta H calculation. So setting that up, I have negative 125 kilojoules divided by 0.048 moles, and that equals then negative 2600 kilojoules per mole. Again, rounded off to just two significant figures because of our all the way back at the start, our delta T calculation having only 2 sig figs. But right, for these types of questions where we have maybe a reaction with not just one as our molar coefficient for our different reactants and products, or we may need to take this kind of extra step in order to account for that molar coefficient. Really like the big difference between this example and the one with the sodium hydroxide from earlier is that this one now has a molar coefficient of 2 for our given reactant. But so again, that just kind of highlights like one more type of calorimeter and the sort of calorimetry-based problems that we'll see with these. In general, right, with a lot of calorimetry, our first thing that we want to do is find the heat of the surroundings. That may be the calorimeter itself, like we have here, or just like water in a coffee cup calorimeter, right? That's usually the first step in these problems. We can then follow that up by equating the heat of our system as opposite of the heat of the surroundings, and then kind of going from there, right? Sometimes the heat of the system we use to calculate like a delta H of a reaction, or sometimes we may just use our Q equals Cm delta T equation again to maybe find an unknown C value. So there are like a few different ways to go about these calorimetry problems, but in general, the first thing you always want to do is find the heat of the surroundings. That's usually going to be the first step in these. But please let me know if you have any questions, and I'm always happy to help. Bye.